In this video, we are going to look at another example about the Hall effect and the Hall probe. Okay, so this question is from Winter 19 paper 42. So let us begin. Electrons enter a rectangular slice of a semiconductor at right angle to the phase PQFE. Alright, so the electrons are going to go in from this side. I'm just going to maybe draw an arrow to represent that. So the direction of electrons is going against the direction of current flow. Right, so your electron will enter this way. So by the time the electron is inside here, it will have a velocity in this direction, drift velocity in this direction. Okay, a uniform magnetic flux density B is directed into the slice at right angles to the phase PQRS. So right angles to this phase PQRS, the direction of magnetic flux density B is pointing downwards. This is B. Alright, setup is fairly common. Let's continue. The electrons each have a charge of negative Q and a drift velocity V in the slice. State the magnitude and the direction. So we want both magnitude and direction of the force due to the magnetic field on the electron as it enters the slice. Okay, so I guess first things first, we can definitely write the magnitude, seeing that the electron is a moving charge. So the magnitude of FB is equal to BQV. You do not need to define the symbols because the symbols are already given here in the question. B, Q, and V. All right. What about the direction? So I think sometimes for some of us, it might be a bit hard to visualize a 3D drawing of this because you're gonna, you may be okay, but if you're not okay with this, I will give you another tip. You could draw a top view from this direction. So basically, you draw a 2D diagram, which is easier for you to think about how your Fleming's left hand will look like when you want to decide which direction the force is acting. So I'm going to draw a top view of this slice. So from here, I can see the phase S, P, R, Q. Okay. Electrons are entering this way. So this is the direction of the electron. So meaning if I have an electron here, negative charge, it will go in this direction V. Magnetic field is going into this plane, going inside the plane. So if I see the top view, it means that the electrons are going inside. So I would then draw a cross to represent the magnetic field. Okay, magnetic field going in. So there will be a cross here. So I'm just going to draw a cross to show your magnetic field. Okay, and now we are ready for our left hand. So a 2D view is more helpful for some people. A 3D view is also fine. You only need to do this if you are confused. So I'm going to use my left hand now. F, B, I. So B is my index finger is B, which will point into the paper or directly into the plane. Okay. Now let's think about my index finger. If the index finger follow the direction of the electron, this is not the direction of current flow. So electron is moving upwards, but current is moving downwards. So we will tilt your hand down like so. So right now, your index finger is going into the plane. Okay, index finger is going in. Your middle finger is going down, going against the direction of electron flow here. And where is my thumb? I find that my thumb is pointed towards the side RQ, going this way, pointed towards the side RQ. So the direction of the magnetic force, FB, will be in this direction. Okay. You can repeat the same idea here for this electron. if you're able to align your hand appropriately, you will find that FB is in this direction. So I think if you can do in 2D, if you can do in 3D, you can do in 2D. All right. So now all the electrons will be directed towards this face. I think I'm just going to highlight this face first. Okay, I will highlight this face. Okay, so the electrons will be directed towards this face, but does it mean that this face must be negatively charged? I don't know. It depends on what the majority charge carrier is. And in this case, it is unclear what the majority charge carrier is. Is it N-type? Is it P-type? Of course, if they say direction of incident electrons and they only talk about the electrons, we could default and say it has to be electrons, right? But I guess I just want to make a note here regarding the polarity of the phase QRFG. Okay? So if the majority charge carrier is positive, i.e. this is a P-type semiconductor, or positive here would simply mean holes, okay? The direction of FB is still the same. You know why? Because we didn't change the direction of current. The direction of current will still go against the direction of electron. This is still the direction of current. So if the majority charge carrier is positive, the force FB on holes is still in the same direction. So the polarity of QRFG is positive. Okay? And similarly, if the majority charge carrier is negative, or electrons, then the polarity of QRFG is negative. So whether this yellow colored phase of the semiconductor is positive or negative, it depends on which one is your majority charge carrier. If your majority charge carrier is holes or positive charge, then that would be positive, because the direction, okay, so what underlies this is the fact that the direction of FB is the same. So I'm going to put a highlight here. I'm talking about this. Positive if majority is hole, negative if majority is electrons. Okay, so the whole fundamental idea here is because your FB is the same direction regardless of electron or holes. So hence, if we want to look at the polarity here, this phase, it doesn't really matter. It's a bit like the direction of FB doesn't change because the direction of current doesn't change. The only difference here is who is carrying the current. Is it the positive charge hole? Then most of the holes will be swept here. This yellow side become positive. Is it mostly electron, the negative charge? Then the electrons are the one that will experience this magnetic force and go to this phase. It depends on the majority. So like it or not, if let's say the majority here are holes, holes will flow in this direction, forward from R to Q. But if you take your Fleming's left hand, for this positive charge moving from R to Q, direction of magnetic force is still the same, because we follow current. Okay, if electron flowing in the opposite direction from Q to R, direction of magnetic force also the same. So the question here is not that the FB change direction, it's what is being attracted to this yellow color phase. Is it the electron? In that case, you're talking about the second case. This phase is negative. Is it the holes? In that case, you're talking about the first case. This yellow phase is positive. So this question, right, I went into this discussion to help explain to you that the type of semiconductor will change the polarity of your Hall voltage. Because right now, I don't know whether this yellow phase is positive or negative, just like I would not know whether the opposite phase here is positive or negative. All right. Okay, so right now, hopefully having both top views and side views and understanding that the direction of magnetic force is the same once we establish the direction of magnetic field and current. Then you just need to know who is the majority charge carrier. The question is perhaps a bit misleading when they use direction of incident electrons, but I think most people will know that direction of current is going against the direction of electron. Has to be what? Okay, so this is a top view. Which color is positive? Don't know. Okay, so just look at the here, no? Look at all this. So it depends on who the majority charge carrier is, because like it or not, whichever is the majority will be swept to the yellow side. Majority positive, yellow side positive. Majority negative, yellow side negative. Okay, we're going to move on now to writing the direction. Direction of this FB is the same, and is I guess parallel to the side PQ and directed from P to Q. Okay, try not to say to the left, to the right, because where is left, right here? Don't know. So follow the sides to help you decide what to write. Okay, you can write PQ, you can write SR, you can write EF, you can write HG. Okay, so just want to put an exclamation point here. No left/right convention. Okay, don't write those things. All right, so the force on the electron causes a Hall voltage VH to be established across the semiconductor and is given by this equation. So the equation that I like to use is BI over net, but they are the same equation, okay? So instead of BI over NET, this Q is equal to your E lah, all right? And the N and T will be the same thing. So state the two phases which the VH is established. So I've already highlighted the phases, the pink and the yellow one. So QRFG and PS, I tend to go clockwise because my maths teacher teach me one. PSHE, QRGF. Okay, so I'm going to go QRGF and PS. Okay, the computer crash. OneNote crash, explaining the color change. Back to the issue. QRGF, so QRGF here, and PSHE. Okay, PSHE. Use the letters in the slice to identify the distance t. So this distance t has to be parallel to the direction of the magnetic field. So let's go back to the diagram. What is parallel to the magnetic field? You can put QF, PE, RG, SH, anything lah. One of these is good enough. Let's say I put SH. All right. So moving on to the next question. Okay. So in the next question, you are given this material called aluminium. So this part, we need to think a little bit about the mole concept. This aluminium has a density of 2.7 gram cm negative 3. So this is density. Okay. This 27 means something. There is one free electron per atom of aluminium. This free electron is your charge carrier. Determine the number of charge carrier or number of free electrons per unit volume in aluminium, or show that it is this number lah. Okay, let's think about what this 27 means. This 27 is the mass number of aluminium. So 27 gram is equivalent to 1 mole of particles, which is equivalent to 6.02 times 10 to the power of 23 atoms of aluminium. Okay, this is what this 27 means. That's why I say the 27 is a pretty important number if you don't know this by now. So if I can find how many moles there are in 1 unit volume, because per unit volume is 1 meter cube. So step 1, I need to find the number of moles per meter cube. And then I can find the number of atoms. And then, because one atom has one free electron, I can find the number of free electrons. Okay, so how do I find the number of moles in 1 meter cube? I use density, because my density, which is 2.5 gram in 1 cm cube. 2.5 gram is 2.5 gram. 2.7 gram, how many mole is 2.7 gram? 27 gram is 1 mole. 2.7 gram is 0.1 mole in 1 cm cube. Okay, so in your working, now you don't have to explain to the examiner what is the mole concept, which I just did on top here, but you should first write this statement. Number 1, 2.7 gram in 1 cm cube, so 0.1 mole in 1 cm cube. Okay, so if we have 0.1 mole of aluminium in 1 cm cube, number 2, in 1 meter cube, there is 10 to the power of 2. In 1 meter, there's 100 cm, 10 to the power of 2 cm. So in 1 meter cube, there's 10 to the power of 2 to the power of 3 cm cube. So you are talking about 10 to the power of 6. So step 3, we can then say, hence, the number of moles in 1 meter cube of aluminium is equal to 0.1 mole for 1 cm cube, but 1 meter cube has 10 to the power of 2 to the power of 3, which is 10 to the power of 6 mole. So this will be 10 to the power of 5 moles. I think I write here, need more space. Okay, so once we know that, then we can move on to step 4. Because if I know I have 10 to the power of 5 moles, so hence the number of aluminium, which is the same as the number of charge carriers or electrons in 1 meter cube of aluminium, will be equal to 1 meter cube has 10 to the power of 5 mole. 1 mole is 6.02 times 10 to the power of 23. This is Avogadro constant. Okay, in case you don't know, or you've forgotten your chemistry, or you haven't studied the gases chapter yet in your A2, this is the Avogadro constant. You can find in your table of constants. So 10 to the power of 5 times 6.02 times 10 to the power of 23, this will give you 6.02 times 10 to the power of 28. Proven or shown. Okay, so what I did was I find the number of mole in 1 cm cube, which is pretty easy because 1 mole is 27 gram, 1 cm cube is 2.7 gram, so you have 0.1 mole in 1 cm cube. But in 1 meter cube, because that's what you want to find in per meter cube, in 1 meter cube, there's 10 to the power of 6 cm cube. 1 cm is 10 to the power of 2. I mean, in 1 meter cube is 10 to the power of 2 cm times 10 power 3. Okay, because 1 meter is 100 cm. So 1 meter cube is 100 power 3 cm cube. So times 10 to the power of 6. We plug this in to the number of moles, okay, because we know that 1 cm cube has 0.1, so 1 meter cube will be 0.1 times 10 to the power of 6. So this 10 to the power of 6 came from this conversion. All right, and finally, we know that 1 meter cube has 0.5 mole, 10 to the power of 5 mole, sorry. Hence, the number of electrons will be 10 to the power of 5 multiplied by the Avogadro constant. All right, so basic mole concept. If you're wondering where the marks are, 1 mark will be any kind of method that makes sense, that allows you to arrive at 10 to the power of 5 mole, and then you multiplying it by the Avogadro constant later. Okay, part 2. A sample of aluminium foil has a thickness of 0.9 mm. This is T. The current in the foil is 4.6 ampere. This is I. Uniform magnetic flux density 0.15 Tesla, B, at right angles to the foil, very nice. Use the value in 1. So the value in 1 is number of charge carrier per unit volume, which happens to be 6. I mean, use the one that is given, 6.0 or 6 times 10 to the power 28. Calculate the Hall voltage VH. They gave you the VH equation already, so that is a very nice bonus, my friends. VH here will be equal to BI over, I guess you could use their NQT because it's a cute equation. Alright, so just don't call your girlfriend NQT lah, although she could be a cutie. Alright, so we're going to now substitute the values inside the equation. Okay, so we are going to now substitute the value of B, 0.15, current is 4.6, just plug and play, bonus question. They already gave you the equation anyway. The equation is here. No? Okay, so I'm just going to use back the equation. NTQ, NQT, doesn't matter. Okay, where are we now? Number of charge carriers per unit volume or charge density will be 6.0 times 10 to the power 28. I will copy the value given in the question itself in part 1. Charge of an electron, 1.6 times 10 to the power negative 19. Thickness, 0.090. Don't forget to convert to meter. So just show all your substitution clearly. That will be your first mark. And then pressing your calculator will be your second mark. Alright, so what I got is 7.896111111 times 10 to the power negative 7. I will write this as 7.99 2SF times 10 to the power negative 7. But CAIE also allow 2SF lah. So you could write 8.0 times 10 to the power negative 7 volt. Okay, so I want you to notice that this value of V is actually quite small. Okay, it's less than a microvolt leh. I think you rub your skin, the voltage generated by the charge redistribution is more than this. Okay, so the way to make this VH measurable could be things like making the current stronger or making the magnetic field stronger. But the reason why this is so small mainly is because of the number of charge carrier. You see, it's offset by this 10 to the power 28. So how do we overcome this 10 to the power 28 leh? We don't use something like aluminium. Conductors are not suitable because you see the thickness is already very thin. So conductors are not suitable as charge carriers. So in case they ask you to comment, I will say small, or they ask you to state and explain why VH is not suitable to use in the lab. In this case, small VH due to large number of charge carrier. So what is the suggestion? Replace the charge carrier. Replace aluminium with a semiconductor. The less charge carrier we have, and the bigger the VH, easier to measure. Okay, so that's all. If you're wondering why the number of charge carriers will affect your VH, it's simply because if it's less charge to attract, this opposing field will take a longer time to build up. Okay, so if you want to know more, go watch the theory video. But this is a pretty thorough Hall effect question. You are starting off by asking us to define the direction of FB and also to decide what phases the Hall voltage will act and which value of T to use. So this part can be made tricky if I tell you the type of semiconductor and ask you to determine the polarity of your yellow phase or pink phase. Even more, one more step to think about. Okay, the second part is to use calculation. So this part where we use the mole concept to find the number of charge carrier per unit volume is a holdback to chemistry. So always calm down when you see mole concept. Just go back to the idea of 1 mole is equal to this, and based on the mass number, the number of grams will be equivalent to 1 mole. and then you just do whatever ratio you need to do. All right. And finally, this part is bonus lah. You plug in the equation, then you calculate. So even if you don't really understand the whole, or you are still struggling with the concept, the calculation part should be okay. But here I'm also explaining to you why VH is very small. Because instead of using a semiconductor, you have used a conductor, which has a lot of charge carrier. If I have a lot of charge carrier, very quickly, there will be equilibrium here already. The Fe build up is fast. So they will cancel up quickly. Okay. For more on that, you can go and watch the video. So hopefully this question was helpful for you to understand the Hall effect. Like, subscribe, share this with your friend, and good luck with your studies. Things are getting hard now, isn't it? Take care. Bye-bye.